Our next lab. Today, what we're going to be talking about is analysis involving categorical dependent variables. So this is going to be a lot of talking about what logistic regression is. And Gemma is here with me as well, and she can, yeah, and then we're good to go. And you can switch the slide whenever you're ready.
Right.
So to start off, logistic regression is used when we have a categorical outcome. Specifically today, we're going to be working with binary outcomes where they only have a 0 and 1, but there's also multinomial logistic regression where you have categories that are 0, 1, 2, 3, 4 that are all categorical variables. But essentially what's going on with logistic regression is that you're using this thing called a logit link to link your categorical outcome variables to your predictor variables. And what it'll actually do is when you take this logit link, it takes this kind of S-shaped curve that a binary outcome would normally have and turns it into a more straight line slope so that we actually are working with a generalized linear model is what it's called. And from this, you're able to derive these interpretable odds ratios from the logistic regression. And we're going to learn a lot about odds ratios and why they're so important throughout the lecture. Okay.
And so there are a few different probability terms that are important to the concept of logistic regression. So as Neil said, logistic regression basically allows us to interpret the odds or the relative risk of an event happening. And so a couple things just to go through quickly. So a proportion can be an estimate for probability. So for example, if 75% of students who studied received a passing grade, the probability or risk of randomly polling a student who studied getting a passing grade is 0.75. Our risk ratio allows us to compare the probability across multiple groups. So you can compare the probability of someone in group 1 having an outcome versus the probability of someone in group 2 having an outcome. Odds ratios are what we're going to be working with in logistic regression. It's another way to describe the likelihood of an event, and it's basically saying the chances that an event will occur versus a chance that an event will not occur. So the odds of someone having experienced, for example, a passing grade versus not.
All right. So today we're not going to be working with any new packages. These should all be packages you're familiar with. The tidyverse package, the psych for describing your variables and looking at them, and the OLSRR package for displaying regression output. Okay. And the data that we'll be using today is just a simulated data set. It's called logistic2.csv. It's got 164 observations of 5 variables. And our y variable is actually a binary categorical variable where 0 is the event not occurring and 1 is the outcome occurring. And then we have 4 other variables as well. X1's a binary variable, and the rest of them are continuous variables that we'll be working with.
So just a quick outline of what we're going to do today. Like we said, today is categorical outcomes. So we're going to regress our categorical outcome y and all the predictor variables in 2 different ways. First, we're going to use our OLS regression, what we've already done in the past. Then we're going to use logistic regression, and we're going to compare the results from the 2 approaches. And what we'll see is that we'll get pretty similar results, but logistic regression interpretations are way more concrete and easier to work with. Also, we're not going to walk through the steps of doing descriptives or visualizing your data. Just know that this is advised if you're actually working on real data. So part 1, we'll go through our OLS regression steps.
So pretty much what we're going to do starting off is we're going to be doing this in a hierarchical regression approach, right? So we'll start off with using our outcome of y and regressing it on x1. And then we'll see kind of how it works out, and we'll keep building on top of that and comparing our R-squared values. So this is what our regression is, where we have y regressed on x1 and pulled out. So you'll see that the interpretations are a little bit odd when you're doing OLS regression on a binary variable, but the intercept is when x1 is 0, the expected y is 0.500. It's a little odd working with to understand overall, but it's okay. But overall, this model explains 19.31% of the variance in y. Yeah, and we're not going to be working with interactions in this activity either, so don't worry about that. So we're going to go ahead and go to the next model where we build on top, and we just add our x2, and now what we're seeing is that this model is explaining 19.58% of the variance in y, which really isn't much higher than our variance explained in model 1, which was 19.3%. So really we're not adding much by adding in our x2 variable.
Mm-hmm.
And then we can go ahead and move on to our next one where we add in the x3 variable. And really, again, we're seeing again, this model explains 21.64% of the variance in y, which really is not even any higher than model 2, really, which was our 19.58%. So really, by adding in the x3 variable, we're not adding in much explained variance. And then finally, we go into the x4, we add in our x4. And just so you know, we have all the interpretations for each of these within our, on the right side, but we're not really going to go over the interpretations so much. We'll talk about that more with logistic regression to kind of get you on better board with that. But overall, when we add in the x4, this model explains 26.87% variance in y, which is larger than model 3, which I would say seems like quite a bit more variance explained than model 3. So really, we're seeing that, you know, models 2 and 3 didn't explain very much. However, model 4 really did seem to explain a lot more of the variance in y.
Mm-hmm. And, you know, when you do look through these interpretations, just note that, like Neil said, they are a little bit odd. So our y variable, remember, it's yes or it's no.
Mm-hmm.
It's 0 or 1. So saying, for example, that a 1 unit increase in x4 controlling for the others leads to a 0.115 increase in y doesn't actually tell us very much about what group someone's likely to be in.
Mm-hmm.
So just a quick summary about what we pulled. Here we wrote up the percent of variance explained from the R-squared values of each model. Like Neil said, it's really only the fourth model that adds x4 that really adds to the variance. The R-squared gives us an effect size estimate for how much variance is explained. You can also do a significance test if you want to, using the ANOVA function for hierarchical comparison, like we've done in the past. And you'll see, just like we saw from the effect size that Neil talked about, it's, you know, adding the x3 does seem to add a significant amount of variance explained, and that's to a greater degree when we add the x4 model. All right, moving on. Now we're going to start doing the same set of analyses, but with logistic regression instead.
Mm-hmm. Yeah, so to do logistic regression, we're going to be using something called the GLM function. This is very similar to the LM function. However, remember, because we're working in logistic regression, we're working in these generalized linear models, which is what the GLM stands for. So to start, this works just like your other regression models where you use the y variable and use the tilde to regress it on any of your x variables. Here we're regressing on all 4 x variables. And then we indicate something called family. And we say we want the family that to be working with is binomial. And what that means is that our outcome variable is binomial. It can only take on 2 levels, a 0 or a 1. And then, of course, we, as always, did it indicate the data set as well. So then we take the summary of that GLM object that we just created, and we'll see the following output.
And just really quick, the GLM function has so many uses outside of logistic regression, and where you really specify that is in the family function. There are a lot of different outcome distributions that you can specify there.
Yeah.
All right, so taking a look at our model. Now, one thing to note at first, here we did not build up the model in a stepwise way like we did before. And the reason is that, we'll show you in a few slides, we can back calculate the amount of variance explained in each step later on. But here's our output. You'll see it looks kind of similar to the OLS regression that we have our slope estimate and our significance levels. But the important thing to note is that the units here are in log odds. We can see that they're significant, but basically we're saying for 1 unit increase in x1, controlling for the other ones, the log odds of being a 1 versus 0 increase by 1.77. Not that useful, so we're going to exponentiate our coefficients, which will give us the odds more interpretable.
Yeah, so In order to, so as Gemma said, we're going to exponentiate our coefficients and our confidence intervals actually, so that we can assess the confidence intervals. So to do that, we use the something called the exponentiate function, which is just exp for short. And we actually use another nested function within that called coefficients. And what that's going to do is going to pull all of the coefficients from your logistic regression model, the one that you created from the GLM function, and it's going to exponentiate them. So if Gemma, you actually can go to the next slide. Yep. And what we're doing here is we're exponentiating first the coefficients, and then in the red, we're exponentiating the confidence intervals as well, so that we can have odds ratio confidence intervals around the actual odds ratios themselves. So in the blue, oh, sorry, go back. So in the blue, I've actually highlighted where all the odds ratios are. So for the blue, is that blue line of code created those first set of numbers, which were the odds ratios, and then the red line of code indicated the confidence intervals. And then now we can go to the next slide. Cool. Yeah, so really, we can kind of, now we're able to have the actual interpretations of our model here too. So the intercept is interpreted that when all the, it's very similar to how we were doing the OLS regression, but when all the x variables are 0, we're now saying that the odds of developing whatever the outcome of y is 0.421 times as likely as 0.421 times as likely to be developed. However, we can also take the inverse of that, which I like to do whenever your odds ratio is below 1. And we can take the inverse, and we say that the inverse states that they are 2.3 times likely as likely not to develop the outcome of y. Additionally, we can figure out that this is not statistically significant by looking at the confidence intervals for the intercept. And you'll notice that the intercept for this is 0.05 to 2.89. Now, notice that that actually contains the value of 1. Before, you learned in OLS regression that containing a interval of 0 means that it was not statistically significant. However, in odds ratios, it's actually if it has a containment of 1 that makes it an indication that it's not significant. This is because 1 indicates that there's no difference between the two groups. Moving on, we can talk about our other variables as well. So our x1 variable, we have an odds ratio of 5.88. So really, that's a binary variable. So we're saying that after controlling for all the variables in the model, very similar to how we normally interpret regression, those coded as 1, so those that have an x1 variable of 1 are 5.88 times as likely to develop the outcome of y as compared to those coded as 0. And this is statistically significant because we can look at our confidence intervals and see that it doesn't contain the value of 1, from 2.37 to 16.22. Yeah, and so essentially that's what we do. And something else I want to say about that.
I think I'll just jump in quickly. You can look at the other interpretations here. Yeah. The other ones are continuous, so instead of it being in group 1 versus group 0, it's for 1 unit increase in these predictors. But the really main takeaway is that these are really concrete interpretations. Yes. So for example, being able to say that an increase in a certain variable or a certain construct makes someone a certain amount of times more likely to experience an outcome can be really meaningful for psychology. Mm-hmm. For example, if you're doing research in substance use and you want to know who's most likely to benefit from this treatment, or who's most likely to experience a negative outcome from trauma versus other people, this gives us some really concrete statistics to work with. Anything else, Neil?
No, I think that's actually it. That's really great.
Great. All right, so we looked at the overall interpretation of each effect in the previous slide. And another thing that we can do in logistic regression is evaluate model fit with something called deviance testing. And what deviance is, it's an estimate of model fit in which we're going to compare each subsequent model to the null model. The deviance values themselves aren't actually meaningful, but lower values indicate better model fit compared to the null model, which wouldn't include any predictors. And so what we're actually looking at, it just lists x1, x2, x3, x4. What the table actually means is it's just like similar to hierarchical regression, we're comparing each subsequent model. So we're comparing the model with just x1 to the null. X2 row is comparing the model of x2 and x1 versus the null model, and so forth until x4 is the full model to the null model. And so the significance levels here are telling us whether adding information to the null model basically leads to a significantly better prediction. In this case, it's the x1 and the x4 models that seem to add the most important prediction information. X2 and x3, not so much.
Yep.
So something that we can do here, in the OLS models, we get an R-squared. That is our effect size for comparing the amount of variance explained across models. And we can get a really similar estimate here with something called the McFadden's R-squared. It's not an exact R-squared, but it gives us an estimate of the percent variance explained by each model. And we can calculate that using this simple formula, where the McFadden's R-squared equals 1 minus the deviance of the model divided by the deviance of the null. And we highlighted in blue where you get that. So for example, for the model x1, it would be 168.72 divided by 203.32.
And really, this slide is just showing us the calculations and how we manually entered them in. So if you go back to the last slide, you'll see where we pulled the numbers in. Yep, so you'll see where we got the deviance null, which is always consistent of 203.32, and the deviance of the effect, and you subtract 1 from that entirety. And so we get the percent variance explained in Y for each of our models here. So as you can see, it's similar to our OLS regression. It goes slightly up. You see this kind of stepwise increase in the R-squared. Going from model 1 to model 2 doesn't seem to add too much. Model 2 to model 3 adds a little bit. And then, of course, model 4 seems to be adding a lot of the variance explained in Y.
Yeah, and so this is why when we said we don't need to build up the model in the same way as an OLS, this is where we can go and back calculate the amount of variance explained with each subsequent model. We just have fewer lines of code here.
Yeah. Great, and then all we're going to be doing now is comparing the results from the OLS versus the logistic regression models. As you can see, so we had the percent variance explained in Y, which would be our R-squared values on the left side for our OLS regression, and the percent variance explained in Y for our logistic regression, which was the McFadden's R-squared. And as you can see, the values are quite similar to each other. So we see a little bit of a decrease in our McFadden's R-squared as compared to our R-squared values in the OLS regression. However, we oftentimes prefer to use logistic regression because it provides us that concrete and meaningful interpretations of our coefficients. Because when we're talking about odds ratios, we're able to make these proper comparisons between groups, and I'll talk about how much times as likely from moving from 0 to 1 or 1 to 2, depending whether it's a binary or a continuous variable.
Yeah. I guess the only other thing, I think you might have mentioned this, but we are getting like similar significance results from the models too. X1 and X4 are the ones that are significant in both of these. But like Neil said, the logistic regression just gives us a lot more information that's actually meaningful for understanding our data. All right, that's a wrap.
All right, thank you, everybody.
Thank you.